Good evening, everybody. Welcome to Chem 1211 with your host, me, Dr. White. Hi, everybody. Tonight, I'll be going through the review for test number one. How do you like those special effects? But anyways, I'll be doing test number one. Let me just remind you about test number one. I'll be giving from this Saturday through the end of Wednesday, test number one will be given at the COD, only at the COD Glen Ellen Testing Center. When you go there, you'll need a picture ID and a calculator. They'll give you one if you don't have one. You should bring your own because you know how to use it. Also, bring a writing implement, even though they have pens and pencils there. I'd highly recommend a pencil and a good eraser. All right, test one will cover chapters 5 through 10, and this covers chemical bonding, including ionic covalent bonds. It will cover mole and mole-related topics, including hint, balancing chemical equations. The test has 21 problems, 9 pages. There are no multiple choice, but some of the questions will have multiple parts. It will have 49 points on chemical bonds and related topics, such as electron shell and subshell. And it will have 56 points on mole and mole related topics, including balanced chemical equations or reactions. That's both are the same synonym. And a fancy word from Dr. White. And if you add it up, it adds up to 105. So there's five bonus points. Remember on the test, underneath your name, it will say boldly, please use proper significant figures for all calculated answers and use three significant figures for all atomic masses. By sometime Sunday, I should have your scores posted in Blackboard. And tonight I'll be giving the meeting, obviously. And I'll be posting this later on. All right. One important tip or recommendation for test number one is show your work. For any problems, show what you're doing. Because if you make a math there, I pushed the wrong buttons here, and just write out an answer and it's wrong, I'll give you 0 points. However, if you show your work and you make a mistake here or somewhere else, I can give you partial credit. So it pays to show your work. Also, let me remind you about the testing center. You may get there when it's busy. They close on Monday, Tuesday, and Wednesday promptly at 5. I'm not sure their hours on Saturday. So if you get there at 4 o'clock or 10 to a quarter to 4, and there's a line in front and it takes a half hour before you get your test, you're not going to get the full amount of time. Now, because that's not a normal classroom environment, because people are coming in and out of the room, instead of normally, if we were face to face, you'd have 55 minutes to do test number one. And because you're there, I'm going to give everybody 2 hours. That's more than enough time. Take your time. If you suffer from test anxiety, I sent out an email a while ago, and it was an announcement to watch the video where I show the method I created that eliminates test anxiety. If you can't find it, email me and I'll send you the link. And I guess it's time to get going. All right. Now, even though it says fall 2022, it's valid for the semester too. If you go to the to Blackboard, let's go there. And on the right, on the left, you see course information. Click on lectures. And scroll all the way down somewhere. All right, where did I hide it? Here we have Chem 1211, Test 1, Review Fall 2022. It's good for this one. I have it both as a document, Word document, and a PDF file. Now, the other thing I have here is important information, test number 1, and these 2 pages will be given to you on the last page, 2 pages of your test when you take it. And that way, you can, let me just open this up so I can, oh, that's not what I want. And this is stuff you don't have to memorize, which in the past I used to have students memorize. But again, the review that I'll be going through tonight is located in the lecture folder of the content area of Blackboard. All right. Starting out, I talked about electron shells. Those are the areas where electrons exist that have essentially the similar energy, not the same, similar. And the shells have very difficult names, 1, 2, 3, 4. Now, shell 1 has 1 subshell, 2 has 2, and so on. Now, I don't have here, but it's something you got to remember. And shell 1 is the lowest energy. That's the electrons there have the lowest energy. And as you go out to shell 2, 3, and 4, the energy of the electrons increase. And Mother Nature, by the way, if you don't know, Mother Nature is the greatest of all chemists, really. And you always fill the lowest shells before you fill the higher ones. Now, when we look at subshells, the subshells, say that 5 times quick, no, I don't, have the letter names S, P, D, and F. And S is the lowest, F is the highest. Here's another way of saying that. S is the lower energy, less than P, D, and F. And here I have it in a table. Again, S is the lowest energy subshell. And as we go down, it gets higher, and F is the highest. Now, you always fill the lowest subshell in a shell before the other ones. Now, important part of this table, and I really should have this max number of electrons. Shell 2 can only take 2 electrons, P6, D10, F14. Why? Well, it's not an area I studied, but that's what it is. That's what chemists have figured out. And this is true for all elements. Now, one of the things you should know how to do, hint, is draw the electron configuration for certain elements. And I'll never ask you on a test, what is the electron configuration? But you should know how to do that. And hint, it deals with numbers, letters, and then superscript, that means above higher numbers. So let's take a look at one of these. Now, let me take a look at my periodic table. Oh, I got one I haven't done in a while. So the question is, what is the electron configuration for neon? Well, first of all, you have to find how many electrons does neon have? Well, let's go back to our friendly neighborhood periodic table. You will be given a copy of this. It won't be green, probably be print, and it will have here. And neon has the chemical symbol Ne. You have to learn that for test one. And you also learn that the number in the upper right-hand corner, the atomic number, gives you the number of electrons and protons, in this case, 10. So we now know we have 10 electrons to deal with. The first shell is 1. You always start at the lowest energy, that's 1. 1 has 1 subshell, and the lowest subshell is 1s. Remember, a subshell is designated by a number and a letter. A subshell is designated by a number and a letter. So the only subshell in 1 is 1s. What's the maximum number of electrons we can put in a S subshell? Well, if you look here, 2. So I'm going to do that. Now, shell 1 has only 1 subshell that you can take 2 electrons. Well, I filled it up. Now I have to go to the next lowest shell and subshell. And again, if we go to important information, if we filled up shell 1, we go to shell 2. And shell 2 has 2 subshells. And they would be S and 2S and 2P. So let's go ahead back to our whiteboard. We've done 2 electrons. We got 8 more to go. So the next is shell 2 and subshell. Remember, subshell letter and a number, 2s. How many electrons maximum can we put in any S subshell? 2. Well, I'm going to do that. Well, that's 4, but I got to get to 10. Well, how many subshells does shell 2 have? 2. And the second subshell, first is S, and the next one, remember you go from the lowest and keep on going higher, always fill the lowest first, is P. So that would be 2P. And how many electrons maximum can we put in any p orbital? 6. Well, I have 4 here. 10 minus 4. Oh, goody. It equals 6. So P, 2P, the maximum I can put in is 6, which is what I need to do, and I'm done. So the electron configuration for neon is 1s, 2, 2s, 2, 2p, 6. Now, if we go on to next sodium, then I'd have to go to shell 3 because we just filled up shell 2. but we're not going to do that. I have done that in the problem set. All right, let's move on. The next thing you should know are the valence electrons. In all of chemistry, to me personally, the valence electrons are the most important. That's where the action happens, the good stuff, the fun stuff. And you should know what are the valence electrons. This is one definition I'm going to ask you to know. And they are the outermost electrons of an element. They're in the very outer part where the electrons are in the electron cloud. Remember, in the center, the nucleus, protons, and neutrons. How do you find the valence electrons of an element? The number of valence electrons for an element is found on the top of the column of the periodic table. So if we look here at our periodic table, if we look at the first column, hydrogen, lithium, sodium, potassium, and so on, the number on top is 1, so they have all valence electrons. In the second column, magnesium and calcium, the valence electrons are 2. Now let's go all the way over here. One of my favorite, carbon, 4. Nitrogen, 5. Oxygen, sulfur, 6. The halogens, fluorine, chlorine, bromine, iodine, 7. And the noble gases, helium, neon, argon, krypton, and so on, have 8. Now, it used to be we just had the Roman numerals, but a couple of years ago I found, guess what? They're no longer teaching Roman numerals in grade school. I think I learned it in second grade. We learned Roman numerals, so I don't do that anymore, which is why I wrote in first black, then red, the numbers, the numeric value. So the number on top for each column is the number of valence electrons, which are the outermost electrons. Now, we show the valence electrons of an element, and I'm only talking now of an element, by using Lewis structures, otherwise known as valence dot electron dot structures. And you first show the chemical symbol, and then you're only talking about valence electrons, and you put 1 on each side before you double up. So if I were to ask you, do the Lewis structure for a compound, let's try one. If I were to ask on a test, draw the Lewis structure for oxygen. First of all, how many valence electrons does oxygen have? Go to your friendly neighborhood periodic table. I stole part of that from Spider-Man. But anyways, oxygen is O. And if we look at the top, we see the number 6, which tells us oxygen has 6 valence electrons. So we have oxygen has 6 valence electrons. You write the chemical symbol, and then you start putting 1 valence electron as a dot on each side. Well, that's 4. Now we have to double up. Now, organic chemists, which I am, always put that's 5 and 6, and that's how we write it. But if you wanted to write it like this, and there are other ways I could do it, that would be perfectly correct. I'd look at it and say, oh, that looks funny, but that's because organic chemists always write it this way. And that's how you do valence Lewis structure for elements using the valence electrons. Next, I started getting some good stuff, and we're talking about chemical bonds. Chemical bonds are the forces that hold atoms of elements together to make molecules. And there are two types of chemical bonds, and you should know the definition. Time for Dr. White to be subtle. Don't you love when I'm subtle? So you should know an ionic bond results from the transfer of one or more electrons from one atom or group of atoms to another atom or group of atoms. That's an ionic bond. The other type of chemical bond is the covalent bond, which, hint, you should know the definition. This results from the sharing, and I somehow started years ago. See, I'm holding hands, sharing. Actually, this is like a knuckle coupler of a train cars. But anyways, Dr. White's a train enthusiast. I have been since I was 5. But anyways, results from the sharing of one or more, and this is important, pairs of electrons between atoms. So an ionic bond, you're transferring one or more electrons from one atom or group of atoms to another. And a covalent, you're sharing one or more pairs of electrons between atoms. Now, there's something called the octet rule, which I'll never ask you what it is, but you should know how to use that in compound formation. In other words, forming chemical bonds for molecules. Atoms of elements lose, gain, or share electrons in such a way that their electron configuration is identical to that of the nearest nearest noble gas or noble gas nearest to them, which is meaning they try and lose, gain, or share, so they get 8 valence electrons. Now, when an element loses or gains electrons, it forms an ion. And how do you know? If I asked you, what ion does calcium form? And calcium, you know how they tell you you should have calcium for strong bones, and Dr. White takes a supplement because I don't like drinking milk that much. But it's not calcium metal. No, you're not going to eat metal, something like that, hard. You have calcium ions. And that's really what makes your bones strong. Well, what ion does calcium form? Well, the first thing you have to do is look at your friendly neighborhood periodic table. Calcium, Ca, has 20 electrons and 20 protons. What's the nearest noble gas numerically by atomic number? You have 2 choices. Argon, 2 away, and krypton, 16 away, which is closer numerically, argon. So calcium, if it's going to form an ion, wants to have the same number of electrons as argon. So it starts out with 20 electrons, 20 protons. You're not going to lose protons. Show me how. We can make a lot of money. But anyways, it will lose 2 electrons to 18. Now, each electron has a -1 charge. Each proton has a +1 charge. Do the math, multiply it. You have -18 plus 20. You add these two together and you get +2. Now, on a test, I'd ask, what is the ion form? And you show the ion by having the chemical symbol, and then to the right superscript, does it form plus or minus? And that you determine when you add this up. Sometimes it's negative for certain elements. And then you write the charge and the number. That's the old way that Dr. White still likes to do. And the newer way, you do the number, then the charge. Either way would be correct. All right. Now, when we talk about the formula of an ionic compound, It indicates the number and kind of ions that make up an ionic compound. Now, something that's very important. And when I used to take notes in college, it was important. I'd put IMP and an arrow, and it was really important. I'd put a couple of stars too, which means when I'm studying my notes, I better know that. All molecules, the sum of all charges in a formula are always zero. All molecules have a net zero charge. It's another way of saying that. And you should remember this. And what does that mean? If we look at this, what is the simplest chemical formula? Or sometimes I'll say, what is the empirical formula of a molecule with sodium cations and chloride anions? Negative is anion. Well, this is a +1 charge, and this is a -1 charge. Does it add up to 0? Yes. So that tells us this molecule, the simplest empirical formula or chemical formula, NaCl, 1 sodium, 1 chlorine, otherwise known as table salt. And the actual chemical name, sodium chloride. And if you ever go out with a bunch of chemists for lunch, breakfast, lunch, or dinner, and I've been guilty of this pretty many times, when someone at that table, a chemist, wants the salt, they'll say, can you please pass the NaCl? NaCl. Never mind. All right, let's look at another one of these. And again, what would be the simplest chemical formula or empirical formula for a molecule of calcium +2, chloride -1 ions? Well, this is a +2, this is a -1, and it has to add up to 0. Oh, no, it doesn't. You cannot change the charge, but you can change how many there are. I'll say that again in slow motion. You cannot change the charge, but you can change how many there are. Students try to change the charge, and it's going to be wrong every time. So if I want to add this to 0, this is a +2, I need a -2. Since I can't change this, but I can change how many. If I have 2 of those, 2 times -2 is -2 plus +2. Now it's equal to 0. And what does this tell us? This has 1 calcium, because when there's no number, that means 1. And this has 2 chlorine. And we show that by the chemical symbol. And to the right, subscript 2. And this is calcium chloride. And those are the little white pellets you throw on your sidewalk when it's super cold, or your driveway, like Dr. White does in the winter, when you want to melt ice and the temperature is below zero. And I'll talk more about that later in the semester. Let's do one more. And this deals with a polyatomic ion. And that's where you have two or more atoms that are bonded together in a anion or cation. And here we have for C, magnesium +2 cation plus, this is called hydroxide, -1. And all molecules have a net zero charge, and that has to add up to zero. Oh, it doesn't. So what do? We take and say, well, this is a +2, this has to be a -2. I can't change the charge, but I can change how many. 2 times -1 is -2 plus 2 is 0. So what does this tell me? When there's no number in front, that means the number 1, there's 1 magnesium. Now there are 2 of the hydroxide, OH minus. How do we show that? When you have more than 1 polyatomic ion, you put a bracket, the ion, close bracket, and when you don't use brackets when there's only 1, but in this case, subscript to the right of the last bracket, you put a 2. And that's how you do polyatomic ions. Now, when we talk about covalent bonds, and we have what's called bonded electrons and non-bonding. The bonded are those that are being shared between atoms, and I'll never ask on a test what's bonded or non-bonding, but you should be familiar with it. Non-bonding electrons are pairs of valence electrons that are not involved in electron sharing. It's subtle time. And let's talk about the types of covalent bonds. The first type is a single bond. And a single bond is a bond in which 2 atoms share 1 pair of electrons. A double bond is a bond in which 2 atoms share 2 pairs of electrons. Remember, a pair means 2 electrons, so 1 pair is 2 electrons, 2 pairs 4. So single bond, sharing a 1 pair of electrons between 2 atoms. Double bond, sharing 2 pair of electrons. And a triple bond, sharing 3 pairs of electrons. You won't learn this class, but if you take my organic chemistry, you'll learn double bonds are very important, fats and oils, and that leads to what we call cis and trans fats. So these are important in our daily life. So let's take a look at how we use covalent bonds. Draw the Lewis structure for nitrogen gas. How do you do that? Well, we're talking about 2 nitrogens And you have to first look up the number of valence electrons. And you go to your friendly neighborhood periodic table. Nitrogen right here has 5 valence electrons. So each nitrogen has 5 valence electrons. Now you can do this in your head or on paper. I like doing it on paper. Here are my 2 nitrogens. Now the 2 electrons pair, those are my non-bonding. But if you look at nitrogen, it has 1, 2, 3 single valence electrons. And this one has 1, 2, 3 single valence electrons. And one nitrogen says to the other, hey, I've got 3 valence electrons. You have 3 valence electrons. Let's share them. And they do. And what happens is the non-bonding electrons are still there on top, but now we have how many? 1, 2, 3 pairs, because each 1 electron. And this is the nitrogen gas you're breathing right now in the air. And what kind of bond, covalent bond, holds the 2 nitrogen atoms together in nitrogen gas? Well, that's 3 pairs of electrons being shared, and 3 pairs of electrons is a triple bond. Now, I'm not going to go through it tonight, but I did it in a video and I've had it in a problem set. If you have both ionic and covalent molecules or atom bonds in a molecule, remember this. The alkali metals, lithium, sodium, and potassium, are never, ever in a covalent bond. The alkali metals, lithium, sodium, potassium, are never in a covalent bond, only ionic. That means they're going to give up their electron to form an ion because they form a +1 ion. Remember that. I'll say that once more. Lithium, sodium, potassium are always forming ions to form an ionic bond in any molecule. Time out for water break. Boy, this chemical bonds is thirsty work. All right, let's move on. Let's talk about one of Dr. White's favorite areas, and that's moles and mole calculations. The moles are one of the most important concepts in general chemistry. You can use moles to determine how much of certain things to use in making molecules, like I have when I've written procedures in chemical plants that make at one time maybe 40 up to 160,000 pounds of a molecule. That's a lot. It's a lot of fun too. But anyways, let's talk about something. What is the mole? And you should know that the mole is the chemist's counting unit. It's like you go into a store, you can buy a dozen bagels. Dr. White loves bagels, or donuts. They're dangerous too. Or things like that. You go into the supermarket, you get a dozen eggs. Well, chemists use the mole. Now, there's some important relationships, and oops, this should be superscript in the test it is. One mole of an element equals Avogadro's number of atoms of that element. you should know Avogadro's number, which I'll give you these things right here, important information. You should know Avogadro, great Italian scientist. I don't think they called them chemists back then yet. Investigated and helped establish the relationship of a mole to different things, which is why this is numbers name, even though two German scientists, which I can't remember their name, most chemists don't, which is sad, actually came up with that number. But it's 6.02 times 10 to the 23rd atoms of an element, and 1 mole of a compound is 6.02 times 10 to the 23rd molecules of that compound. Now, in my videos, and I'm going to go through an example right now, remember to use your good buddy, your good friend, unit analysis. It's been my good buddy since senior year of high school. Wow, that's a long time ago, long time ago. Well, let's look how to use this. And I don't know, say 8 points, maybe 10. And sometime in the future, you see this on a piece of paper. How many moles H2O, you should know is water, are 8.11 times 10 to the 44th molecules of water. As you've seen in my videos, the first thing I like to do when I'm solving a problem, which we're doing right now, is what are we being asked to find unit-wise? And I use a question mark to designate that. And we're given moles of water is what we're trying to find. What are we given? We have 8.11 times 10 to the 44th molecules of water. And once I have this, I don't have to read the problem again. So the only thing I have to start with is this number. And what units do I want my answer to be? Right here. Moles of water. And when I write moles of water, you usually don't put the S there. Even molecules, I sometimes don't even put the S there. So if we have a ratio that we can convert molecules of water to moles of water, what do? Well, it's time for your good buddy, your good friend, unit analysis. Whatever we're trying to get to goes on top of that ratio, the units. Whatever we're trying to get rid of goes on the bottom. What do I mean by rid of? Anything divided by itself equals the number 1, meaning it's gone. So now I'm going to write those units in. And this is where I would ask you, show you this kind of work. In case you make a mistake, I can give partial credit if it's right, some of it. So I'll write moles of water here. I'll have molecules or molecule, you don't have to put the S there, of water. And where do I find numbers to put in there? The key of unit analysis, if you have A equal B, there are two ratios you'll always have. A over B, and not equal, two different ones, B over A. And if you look at important information, test number one, which you'll be given, but I'm going to go just to my right here. You see right here, 1 mole of a compound, that's water, equals Avogadro's number, 6.02 times 10 to the 23rd molecules of wet water. Again, 1 mole of a compound equals Avogadro's number, 6.02 times 10 to the 23rd molecules, which means for every 1 mole of a compound, there's 6.202 10 to the 23rd molecules. Now, before I pick up my calculator, don't pick it up yet, I'm going to check what units I have. Notice I'm going to have molecules, water divided by molecules, and that's going to become the number one. They cancel out. The only units I'll have left are moles of water, which is what I want as my answer. Now I can pick up my calculator, clear it, 8.11, remember blue double E for scientific, 44, and then I'm going to divide by 6.01 blue double E 23, and my calculator gives me this number. There are a few more numbers, but I'm like times 10 to the 21st. Now, as I said earlier, underneath your name, will say, please use proper significant figures for all calculated answers. And this has 3 significant figures. Avogadro's number is a calculated number, and this value we use has 3 significant figures, and the 1 is part of the definition, so that's an exact number and plays no role in this calculation for significant figures. When you do multiplication division, you get the same number of significant figures in your answer as the number with the fewest. In this case, it's 3. So we now have to round this number off to 3 significant figures. Keep the 1, keep the 3, keep the 4. That's my 3 significant figures. The next number, I'll use 7 to round off. Is that 4 or less or 5 or higher? And hopefully I'll pick 5 or higher. So that means I drop these numbers, increase this by 1. And you learned that for test 1. And I'll do that. I still write 10 to the 21st. And that's how you do it. Now let's do another problem like this. So the question is, how many grams of water is 2.734 times 10 squared moles of water? As you've seen me do many times, and hopefully you've been watching the video, first thing I'm going to do is, what am I being asked to find unit-wise? And the answer is grams of water. What am I given? 2.734 times 10 squared moles of water. And this might be 10 points or 8. You see it sometime in the future. So the only number I have to work with is this. Now, what units do I want my answer to be in? And we figured that out right here. Grams of water. And now it's time to use your good buddy, your good friend. Unfortunately, Zoom cuts off part of my whistle. Unit analysis. Whatever we're trying to get to unit-wise goes on top of the ratio. Whatever we're trying to get rid of, unit-wise goes underneath. And now I'll write those units in: grams of water, moles of water. And where do I find a relationship between grams of a molecule and moles of a molecule? Well, this will be an important information. Test number one: 1 mole of a compound equals that molecular weight in grams. And the molecular weight of a compound is the sum of all atomic weights. Again, the molecular weight of a compound is the sum of all atomic weights. So 1 mole of a compound equals the molecular weight, and the molecular weight is the sum of all atomic weights in that compound. So what I need to find is what's the molecular weight of water. And I'll do MW shorthand for molecular weight. Well, it's the sum of all atomic weights. Well, there's 2 hydrogen and 1 oxygen. Well, now I need to find the atomic weights of hydrogen and oxygen, and I'll go to my friendly neighborhood periodic table. Hydrogen, and by the way, let me remind you, underneath your name, it will say, please use proper significant figures for all calculated answers. It will also say, please use 3 significant figures, 3 for all atomic weights. So hydrogen 1.008, the 3 significant figures would be 1.01. Oxygen at 15.999, the 3 significant figures would be 16.0. I'll do the multiplication. 1 and 2 are exact numbers, so I don't have to worry about changing significant figures. Now, the molecular weight, MW, is the sum of all atomic weights. Well, that would be 2.02 plus 16.0. Now, something we haven't used until now is rounding off for addition. And for addition, you get the same number of significant figures to the right of the decimal as the number that has the fewest significant figures to the right of the decimal. Everything to the left, you just add, and that's the number you get. But you change to the right, not to the left. This has 2 significant figures, 0, 2. This has 1, which is a smaller number, and 1. So we keep the 0. Remember, we're only considering to the right of the decimal, and use the 2 to round off. That's 4 or less. I'll drop it. So the molecular weight of water is 18.0. So for every 1 mole of water, the molecular weight is 18.0. And that's where we get those numbers. Now, before I pick up my calculator, I'm going to check to my units. Do I get the right units? And here we have moles of water divided by moles of water. Anything divided by itself equals the number 1, cancels out. Always do that check. We're left now with grams of water. Yay, that's what we want. And now I can pick up my calculator. clear it. 2.734 glue double E, 2 times 18.0. And my calculator gives me this number. Actually, it says 10 to the 0, 3. Hold on, let me fix this up. And remember, on test number 1, under your name, it will say, please use proper significant figures for all calculated answers. And for multiplication division, you get the same number of significant figures in your answer as the number that you're multiplying, dividing, that has the fewest significant figures. This has 4 significant figures. 1 is the definition, so that's an exact number. And this has 3 significant figures. So what's the lowest number? 3. So we have to round this off to 3 significant figures. Keep the 4, keep the 9, keep the 2. Use the 1 to round off. Is that 4 or less? Yep. So I drop this and this. And my correct answer here and that's how you do this. And you should know how to do this type of problem. Now, next thing I talked about was the chemical equation. And you should know that everything on the left are called the reactants. And sometimes during the semester, since I worked in the chemical industry for many decades, we also call starting materials. At the head of the arrow on the right, at the head, we have the product or products. So A and B are the reactants in this chemical equation. C is the product. Sometimes you have more than one product. Now, important aspect, and it's called conservation of matter. You never destroy atoms when you do a chemical equation. What you do is rearrange them and things like that. So what that means is when you have a chemical equation, and this is called balancing it, you have to have the same number and type of an element on each side of the chemical equation. And the thing is, when you're balancing it, the number in front, and I'm going to show you this in a second, is called the coefficient. You can't change the chemical formula. Students try and do that. No, only the coefficient. Now, I have found that when you are balancing chemical equations, leave hydrogen, oxygen last. You don't have to, but it makes your life so much easier, and you always helps you get the right answer. The other thing I taught in the videos was the even odd trick, and you should go back and look at that. Let's do one quick balancing chemical equation. This is called combustion when you burn something with oxygen. This is pentane. And the question is, balance the following chemical equation. Now listen carefully. If I ask you to balance a chemical equation on a test, you will have to balance it. On a test I give, any test I give, the answer it's already balanced will never, ever be correct. I'll say that again. When I ask you to balance equations, the answer it's already balanced will never be correct. Now, in the lab you have that's due Saturday that I took from some other sources and put together, some of those may be already balanced. But on a test, if I ask you to balance something, you have to balance it. All right, let's do this. There are 5 carbons here. Notice the number there. On this side, there's only 1. How do I get 5? The number in front, called the coefficient, you can change. So I'll put 5 there, and now I have 5 carbon. So it's balanced on both sides with carbon. Well, all we have left are hydrogen and oxygen, so I might as well start on that. And I'm lazy, I'm going this way. So we have 12 hydrogen. Uh-oh, we only have 2 here. How do we get that to 12? You cannot change the formula number, but you can change the coefficient, the number in front. 2 times 6 or 6 times 2, I now have 12 hydrogen. Now on this side, I have 2 oxygen. How many on this side? Well, 5 times 2 is 10 oxygen. You have to count all the oxygen, all the molecules. And 6 times 1 is 6 oxygen, which means I have 16 oxygen. Well, in order to get 16 oxygen on this side, I'll put an 8 in front. 8 times 2 would be 16 oxygen. And now before I go away, I'll check my math. 5 carbons, 12 hydrogen, 12 hydrogen, 16 oxygen, 16 oxygen. Yay, it's balanced. And you should know how to do that. Hint. Now, the last 2 problems I like to go through, one of them is called mass calculation. Think of mass being grams for a reaction. And there are 3 steps. And let me show you a problem. The 3 steps are whatever you're given initially of a molecule, the mass, grams, you have to convert to moles, which we've shown how to do. Next, you have to convert the moles of what you just calculated to moles of the answer you're trying to get to in grams, B. And now you have moles of B, and you have to convert moles of B to mass of B. And remember, the coefficients of a balanced chemical equation are mole ratios. And let me show you. First of all, I got to open it up. All right, and what I'm showing you is Chapter 8, practice problems. And the question is right here, for the following reaction, C3H8, by the way, that's propane, the stuff in the white container for your barbecue, reacting with oxygen to give carbon dioxide and water. And the question is, how many grams of C3H8 are needed to make 24.6 grams of CO2? So what we look here and say, what are we being asked to find? Grams of C3H8. What are we given? Grams of CO2. You cannot go from grams of one compound to grams of another in one step. You cannot go from grams of one compound to grams of another in one step. You need 3 steps. What are those 3 steps? these right here. Whatever you're given the mass, and remember mass is really grams, of initially A, that's in this case what we're given, you convert to moles of A. Next, you convert moles of A to moles of B. And finally, you convert moles of B to grams or mass of B. And let's see how we do that. All right, so the first step, we're going to go grams of A, and the only thing we have grams of is CO2. And we want to go to moles of CO2. And we'll use our good buddy, our good friend, unit analysis. Whatever we're trying to get to, the units go on top. Whatever we're trying to get rid of, the units go underneath. And where do we get the relationship between 1 mole of a compound and its molecular weight? And this is an important information. 1 mole of a compound equals the molecular weight in grams, and the molecular weight of a compound is the sum of all atomic weights. So we need the molecular weight of carbon dioxide, CO2. There's 1 carbon, 2 oxygens. If you look up, and I don't have this here, I'm sorry, I did it real quick here. Each carbon is 12.0. Each oxygen is 16.0 times 2 is 32.0, and you get 44.0. And therefore, for every 1 mole, you get 44.0 grams of CO2. Grams cancel out. I'm left with moles of CO2, which I want in the first step. This is 3 significant figures, 3. My answer is 3. Now, I have to convert, second step, moles of A, in this case A is CO2, to moles of B. We're trying to get to C3H8. And now you use my good buddy, my good friend, unit analysis. Whatever I'm trying to get to, the moles go on top, moles C3H8. Whatever I'm trying to get rid of, moles of CO2, go underneath. Where do we get these numbers? The coefficient, the number in front of a molecule or atom in a balanced chemical equation, gives you molar quantities. The coefficient, the number in front of a balanced chemical equation, gives you molar quantities. And when there's no number, that number is 1. So what this balanced chemical equation, and by the way, for these 3-step equations, I'm going to give you a balanced chemical equation. No, I don't have anything in my eye. But anyways, what this tells me is 1 mole of C3H8 reacts with 5 moles of oxygen to make 3 moles of CO2 and 4 moles of H2O water. Again, the coefficient in front of the molecule or atom in a balanced chemical equation gives you the molar ratios, how many moles. And when there's no number, it's the number 1. I like those special effects. Anyways, so where do we get these numbers? For every 1 mole of C3H8, how many moles of CO2 are there? 3. 1, 3. Now, these numbers are both exact numbers. The coefficients of a chemical equation are always exact. Just like I can't say, hey, why don't you go outside and find me 3.5 people? No, you're not going to do that. Or 4.2 cars. No, those are going to be exact numbers, just like with this. So 3 significant figures, 1 exact number, 3 significant figures. Notice moles of CO2 divided by moles of CO2 cancel out, and you get moles of C3H8. Now, the third step is because we want grams of C3H8, not moles. We'll start with moles of C3H8. We want to go in one step with some ratio to grams of C3H8. Whatever we're trying to get to goes on top of the ratio. Whatever we're trying to get rid of goes underneath. And remember, this will be given to you important information. 1 mole of a compound equals the molecular weight of that compound in grams, and the molecular weight of that compound equals the sum of all atomic weights. So we need the molecular weight up here of C3H8, propane. Well, I have that right here. Propane has 3 carbons, 8 hydrogens. And let me just show you, you need the atomic weight of carbon, and the 3 significant figures, 12.011 is rounded off to 12.0. Hydrogen, we already did 1.01. Remember, the number underneath the chemical symbol is the atomic weight, and on test 1, it will say, please use 3 significant figures for all atomic weights. If you don't, I'll take off a point. Same thing if you don't do significant figures for your answer. I'll take off a point. So I have 3 carbons, each carbon 12.0, do the math, 36.0. I have 8 hydrogens. 8 times 1.00 is 8.08. And you add it up, you get, it's hard to see, but that's 44.08. Remember, you get the same number of significant figures to the right of the decimal in addition as the number with the fewest. 36.0 has only 1, the 0. 8.08 has 2, 0 and 8. The lowest number is 1, so you keep the 0 here. The 8 you use to round off, is that 4 or less or 5 or higher? 5 or higher. You drop the 8 and the number in front, 0, you increase by 1, so that's 44.1. And 1 mole of a compound equals the molecular weight, and that's why I put the 44.1 on top. Before I pick up my calculator, I will check units. Notice moles of C3H8 divided by moles of C3H8 cancel out, become number 1. I'm left with grams, and do the math. 3 significant, 3. My answer is 3 significant figures. Now, notice I have here or. What I didn't mention is when you have a multi-step calculation like this, there are 2 philosophies for rounding off the whole thing. One is round off at each step. The other is round off at the end. Dr. White is a round off at each step person. However, I'm not going to force you to do that. You can round off at the end. You round off at each step, you get 8.18. If you round off at the end, you get 8.20. Which is the correct answer on my test? Either one. And now the final thing I want to talk about is limiting reactants. That's when you're reacting 2 things and one of them runs out first. If I were, I'm trying to, if I were a company and I made this stylus for my tablet with this cap, you need 1 of these and 1 of these to make a whole unit. Well, if I have 10 of these and only 5 of these, I can only make 5 of these, then I run out. And that's what we mean by limiting reactants. And let's take a look at a reaction or how you do that. And what you do is determine the number of moles of product using moles of each reactant. The lower number of the number of moles of product produced is the correct answer. All right, let's look at number 10 from chapter 8. For the following balanced chemical reaction, it's always going to give you balance. When I was an undergrad, you first have to check if it was balanced. I had a sneaky chemistry teacher. But anyways, how many moles of carbon dioxide are made when you react 2.35 moles of C3H8 with 10.2 moles of oxygen, O2? So what are we trying to find? Moles of CO2. When you're given a balanced chemical equation in moles, that's going to mean you need two steps. In the first step, and by the way, we're trying to find moles of CO2, we're given moles of C3H8 and moles of oxygen. Well, you have to do two calculations. The moles of each reactant, how many moles of product will you get? CO2 is the product we're interested in, not water. I could have done water too. So we have 2.35 moles of C3H8. We want to get to moles of CO2. Use your good buddy, your good friend, to figure out what would be this ratio. You multiply this by. Whatever I'm trying to get to goes on top, moles of CO2. Whatever I'm trying to get rid of, moles of C3H8 go underneath. Where do I get these numbers? From the balanced chemical equation. For every 1 mole of C3H8, when there's no number, the coefficient is 1, I make 3 moles of CO2. For every 1 mole of C3H8, I make 3 moles of CO2. These are exact numbers. Do the this moles C3H8 divided by moles C3H8 cancel out, and I'm left with moles of CO2, and the answer is 7.05 for that number one calculation. The other one, you do the same thing. Starting with moles of oxygen, how many moles of CO2 will you get? Now watch closely. Whatever you're trying to get to goes on top of the ratio, moles of CO2. Whatever we're trying to get rid of, moles of oxygen, goes underneath. Where do we get these numbers? Relationship of moles of one compound to another in a chemical reaction from the coefficients of the balanced chemical equation. In this case, for every 5 moles of O2, we make 3 moles of CO2. The coefficient are molar relationships. For every 5 moles of O2, we make 3 moles of CO2. For every 3 moles of CO2, we need 5 moles of O2. Those moles of O2 divided by moles of O2 cancel out. I'm left with CO2 moles, which I want. 3 significant figures, 3 and 5 are exact, and I get 18.4. To figure out which is the right answer, the lower number of these two is the one you'll get. In this case, I hope you all know 7.05 is lower than 18.4, and the correct answer is 7.05. And I have other problems. I show you how to do that. And with that, I'm done. Let me remind you, you have this Saturday, let's see, the 19th, let's see, today's Thursday, 18th, yep, the 19th, through next week. And let me look at a calendar just to be safe. You'll have from the 19th of October through the 23rd of October. Again, the 19th of this month through the 23rd, next Wednesday, to take test number 1 at the COD and only at the COD Glen Ellen Testing Center. They close at 5. I think they open at 9, but you should check on Monday, Tuesday, and Wednesday. And I think they're 9 to 2, but check on Saturday. And don't forget, you'll need a picture ID. Bring your own calculator. They'll give you one, but bring your own because you know how to use it. I'd bring a pencil or two. Bring your own or good eraser. These are the best. And show your work. Take your time. And with that, I'm done. Oh, excuse me. And as you know, what I'm going to do now, oh, I got the hiccups. Moles do that to me. No, they don't. But anyways, what I'm going to do, you know what I'm going to say? Gain gesund, go in health. That's what it means in Yiddish, gain gesund. And I'll stick around if anybody has any questions after I sign off. If that, thank you, Bianca. I'll say gain gesund. Goodbye now. I stole that.
Thank you.
Thank you. I stole that from Granny to Beverly Hillbillies.